The most incomprehensible thing about the universe is that it is comprehensive. Albert Einstein. Right. Last time we talked about the electroweak theory, the theory of Weinberg and Salam that puts together electricity, magnetism, light, and the weak force of nature, and all the associated particles and force carrier that makes a coherent mathematical framework. Today, I don't want to talk about anything new. We've learned an awful lot of particles and an awful lot of concepts, and I just want to try to consolidate everything that we've been talking about. We have now come to the stage where we really can talk about the standard model in its conceptual fullness. I want to talk about some of its successes, experimental and a little bit more abstract successes. That's really the plan for today, just to take a step back and look at this intellectual achievement that the human race has made. You know, I view this as on a par with the collective works of Shakespeare or something that nature, where we really have come up with something that's very profound and very deep and in principle relatively easy to understand, although the details are some tough going. Let me begin by reminding you of what I mean by the standard model. We have a set of quarks, 6 of them, and we have a set of leptons, 6 of them. Each one of these is considered to be a fundamental particle of nature. It has a certain properties which we just list. You can imagine tabulating these things: an electric charge, a weak charge that's a part of the electroweak theory, a mass, a spin, and not much else. That's pretty much the kind of the properties that you have to attribute to these points. Those are the fundamental building blocks of the everything and anything. Think about this for a second. Think about the enormous complexity of the world around us. Everything from the hardness of the table to the softness of human skin, to the almost the ethereal nothingness of the air around us. The colors that you see, the light that strikes your eyes, the sounds that you make. All of that stuff can be understood coming from just the rules and prayers of the standard model. The rules are these theories: quantum chromodynamics and the electroweak theory, or Weinberg-Salam model, as it's also called. And let me throw out the kind of the full-blown techno bubble at you. It's a renormalizable relativistic quantum gauge field theory. Okay? So let's talk about those words. We can unpack those words because we really already have talked about all of them. Right. Renormalizable is a fancy mathematical statement that say if you include all of the subtle quantum mechanics, you start to get, in the principle, some infinities. You are adding a whole bunch of progressively smaller and smaller collections that add up to be not just big, but infinitely large. But renormalizable means we can sweep it all under a rug. We pay one little price, which is that there are few things that the standard model cannot predict. We have to go out and measure them, but everything else is completely finite. We use Feynman's rules, and we can calculate anything we want. Renormalizability is a condition on any theory of nature. At least it's a so far being an incredibly useful condition because it means that it's mathematically consistent. Renormalizable, relativistic, it has to satisfy what Albert Einstein has told us about the nature of space and time, which includes the symmetries that Albert Einstein has recognized about space and time. Relativistic quantum, it has to satisfy all of the laws of quantum mechanics which were first speculated upon in the early 1900s and then turned rigorous by Heisenberg, Schrödinger, and ultimately Dirac and many other players. Pauli and Fermi and all those characters in the 1920s and 1930s. Quantum mechanics was quite well established by the early 1930s and today really is unchanged. We have been testing it, studying it, and quantum mechanics hasn't continued to evolve in any way. So, a quantum field theory like we are talking about, just has to incorporate all of those laws, such as the Heisenberg uncertainty principle, for example. Quantum gauge field theory, a gauge that refers to the symmetry of nature, a very abstract symmetry of nature that apparently all the forces, all the fundamental forces have. In the beginning, we knew that electricity and magnetism had this symmetry that was observed from the mathematics of the 1800s, and it was such a nice symmetry. It's abstract. I can't talk about it as left-right symmetry or sideways symmetry. It's a little bit more of a mathematical symmetry. Symmetry means you can make a change in what you call things. You can make a change, yet the answer all come out the same. There is an invariance in your theory when you look at it from the different perspective. That's what symmetry is, in its most general sense. It's wonderful and a little bit magical that this gauge symmetry, which we observe to be true for electricity and magnetism, is also true for all the other forces of nature. At least the weak force and the strong force as well. Yes. How do I know that it's a good symmetry? Because we imposed it on the theory, and now we've been tested the consequences of the theory in the laboratory, and it keeps working. Working. That's how it is that I can make the statement that apparently the strong force of nature also has this symmetry. Gauge field theory means that we have this mental image of how it is that you can get action at a distance, how a particle over here can communicate with a particle over there. We visualize the space as being filled with fields. Everything in this quantum field theory is a field. Normally, I think of the forces as a being force field. But in fact, all of the particles are, in a certain sense, equally particles, the electron as much as the photon. There is an electron field in the universe as well as a photon field. This is a theory, a renormalizable, relativistic quantum gauge field theory. It's quite a mouthful, and it's really what we've been spending a good part of all of the lectures so far trying to understand. It's fancy mathematics, but in the end, the story is really one that you can think about in the theory concrete terms. This theory has been successful on a lot of levels. I would call it a successful aesthetically, mathematically, and physically, and I'd like to talk about all three of those dimensions. Wow. First of all, I'll discuss aesthetically. This theory has built into it essentially every symmetry of nature that we have been able to think of, that you might hope that the universe has. We put it into the theory and it makes it very compelling and very appealing. It's also a minimal theory. It may not look minimal, but and it's a little bit hard when you have been working with this for your whole career to step back and ask if this really is simple. To me, it's extraordinarily simple in the sense of just having a few ingredients and a few ideas behind it. And minimal meaning, I guess, that for Mr. Weinberg in 1967, he had to write down a mathematical theory. In principle, you can write down a really complicated theory to describe the weak interactions. Not he chose to write the absolutely simplest one he could. Every time he had a choice whether to make up a new particle, he chose to go with the fewest number possible. We've observed the 6 quarks and 6 leptons in the laboratory experiments, so we have to include them. We don't include anything else except for the Higgs. The Higgs has not yet been seen, and we'll come back and talk about it. It's a sort of the one mysterious piece, actually, of the story. With that one possible exception, it is a truly minimal theory. Wow. You have to think about how amazing it is. In 1967, this theory was published and it hasn't been tweaked in any significant way since then. You introduce a minimal theory, usually the physicist's first idea. Let's just try the simplest one and see if it works. And if it doesn't, he can always add more. We can make it more complicated to try to match the data. That's the way biology, chemistry, geology, and so on often work. Wow. You start with a simple approximation, then you make it richer and richer as you get more and more data, and become more and more precise. Here, we have a rather different situation. We started off with the most minimal theory, and then it just kept working. It kept working even until today. We never had to make it more complicated. Even after we built a new accelerators, we discovered new particles. We learned an awful lot after 1967. But it all fit in with the exact same minimal electroweak theory. So that's a really lovely aesthetic idea that I think compels people to pay some attention to this theory and believe in it as a statement about the scientific truth or nature of reality. It unifies forces of nature, what we thought were completely different forces of nature, electricity, magnetism, light, if you like, the weak force, the weak neutral force of nature. All of those are really one. Wow! In this mathematical theory, it's just one force viewed from different angles, abstract angles. And that's a really lovely idea. Again, there is an aesthetic appeal of this theory. Wow, so sexy. There are some symmetry of nature which are broken in the standard model, and some of them are mysteries, and some of them are deeply understood now because of the theory. For example, left and right are no longer an exact symmetry of nature itself. The laws of physics are different for something spinning like a left hand spins and for something spinning like a right hand spins. They are only different when you consider weak interactions. The laws are the same for electrical forces, strong forces, and gravitational forces. Only the weak force appear to violate the symmetry of nature. That's in the standard model, and I can't explain it to you because nobody knows why. It just is an observed fact of nature. But there are other broken symmetry which we can explain. For example, we have force carriers, then the photon and the Z. They, in some ways, seem like similar things. I mean, they spin one object, and they carry some aspect of the electroweak force, but there is a broken symmetry between them. One of them is without mass, the photon. One of them is a massive, the Z particle. That's an electroweak symmetry breaking. That's a fancy word for that the observed fact of the nature that one of these force carriers has a mass and the other doesn't. We believe we understand that. It arises from the presence of the Higgs particle, which we are going to be talking about. The standard model actually gives you an explanation of why it is that these two forces of nature, which on the one hand seem to be completely symmetrical, but on the practical hand in the real world seems to be so different from one another. If you were to heat the universe, which you could do in a laboratory by smashing particles together, or by going back to the early universe like a Big Bang, you would discover that the weak and electromagnetic interactions are, in fact, identical. Wow! So, the weak and electromagnetic interactions are, in fact, identical. They merge together at super high energies because the standard model has unified them. Those are all sort of lovely mathematical or aesthetic arguments. Wow. Mathematical arguments really boil down to the fact that this theory doesn't contradict itself in any obvious way. If you calculate something, you always get finite answers. There are no probabilities that can be computed in the standard model that comes out bigger than 1 or less than 0. That would be a mathematical inconsistency. Earlier models had that problem, but the standard model doesn't. Wow. So again, all of this stuff is very nice, and to physicists it kind of helps you to believe in the truth of theory. But doggone it. You know, a theory is only good in my mind anyway, and this is a personal opinion. If you can go into the laboratory and make some measurements, calculate some numbers, and compare the numbers you predict with the numbers you get in the laboratory, that, to me, is really what it means to have a correct or successful theory of nature. I'll take a quantitative over aesthetic any day, even if the theory gets a little ugly, if it's a good predictive theory. That is certainly useful science in any case. It may not be the most fundamental or the end of the story, that's all. Every year, the particle data group at Berkeley keeps up a table and a collection of all of the information that we've been gathering over the years. You can go on the web and look up particle data group if you are interested, and you'll find their tabulations. First, there is a symmetry of their standard model that tells you what their ingredients are and what the formulas are. Then there will be a list of the particles. Right. First, the fundamental ones. The electron has this mass and this magnetic strength and this electric charge and so on. Just a table. Every piece of data includes a reference to a paper, a journal article, or maybe several, so you can go and see what experiments were done to give us these numbers. They go on and have tabulations not only of the fundamental particles, but of all the built-up particles such as the pions and the kaons and the protons and the complicated particles in the zoo, which aren't really so complicated after all. They are just 3 quarks put together, or a quarks and an anti-quark. If you look at this, you can get a physical publication of it, and it's a big, thick, fat book. It's a collected information that we have, and each page is incredibly dense because they are not really telling you everything. They are just telling you where to go to find out more details about that particular number and that particular information. It's quite stunning when you think about it. That big, fat book and all of the thousands and thousands of pages to which it refers all comes from the first couple of pages, the standard model, and people have been spending years doing these calculations. To date, I know of no significant discrepancies between the theoretical calculations and the experimental observable. Everybody is looking for it. Everybody would like to find some kind of the crack in the standard model because that's the nature of the physicist. It's no fun just going out and verifying what people are telling you are going to see. It's much more fun if you get a surprise, a curiosity, something we don't understand, and of course, these things still happen. They are often in a subtle aspect of the standard model, but at some fundamental level, we keep hunting for cracks and we are not finding them.